In physics, the center of mass of a distribution of mass in space is the unique point where the weighted relative position of the distributed mass sums to zero, or the point where if a force is applied it moves in the direction of the force without rotating. The distribution of mass is balanced around the center of mass and the average of the weighted position coordinates of the distributed mass defines its coordinates. Calculations in mechanics are often simplified when formulated with respect to the center of mass. It is a hypothetical point where entire mass of an object may be assumed to be concentrated to visualize its motion. In other words, the center of mass is the particle equivalent of a given object for application of Newton's laws of motion. In the case of a single rigid body, the center of mass is fixed in relation to the body, and if the body has uniform density, it will be located at the centroid. The center of mass may be located outside the physical body, as is sometimes the case for hollow or open-shaped objects, such as a horseshoe. In the case of a distribution of separate bodies, such as the planets of the solar system, the center of mass may not correspond to the position of any individual member of the system. The center of mass is a useful reference point for calculations in mechanics that involve masses distributed in space, such as the linear and angular momentum of planetary bodies and rigid body dynamics. In orbital mechanics, the equations of motion of planets are formulated as point masses located at the centers of mass. The center of mass frame is an inertial frame in which the center of mass of a system is at rest with respect to the origin of the coordinate system. History. The concept of center of mass in the form of the center of gravity was first introduced by the ancient Greek physicist, mathematician, and engineer Archimedes of Syracuse. He worked with simplified assumptions about gravity that amount to a uniform field, thus arriving at the mathematical properties of what we now call the center of mass. Archimedes showed that the torque exerted on a lever by weights resting at various points along the lever is the same as what it would be if all of the weights were moved to a single point, their center of mass. In work on floating bodies he demonstrated that the orientation of a floating object is the one that makes its center of mass as low as possible. He developed mathematical techniques for finding the centers of mass of objects of uniform density, of various well-defined shapes. Later mathematicians who developed the theory of the center of mass include Pappus of Alexandria, Guido Ubaldi, Francesco Maurolico, Federico Comandino, Simon Stevan, Luca Valerio, Jean-Charles Delafaye, Paul Gulden, John Wallis, Louis Carré, Pierre Varignon, and Alexis Clairaut. Newton's second law is reformulated with respect to the center of mass in Euler's first law. Definition. The center of mass is the unique point at the center of a distribution of mass in space that has the property that the weighted position vectors relative to this point sum to zero. In analogy to statistics, the center of mass is the mean location of a distribution of mass in space. A system of particles. In the case of a system of particles pi, I equals 1, n, each with mass m that are located in space with coordinates r, I equals 1, n. The coordinates r of the center of mass satisfy the condition I equals 1, n, m, I, r, I, minus r equals 0. Display style sum underscore I equals 1 caret n m underscore I. Math BF r underscore I math BF r equals 0. Closing curly bracket. Solving this equation for r yields the formula r equals 1 m I equals 1 n m I r I display style math BF equals frac 1 m sum underscore I equals 1 caret n m underscore I math BF underscore I closing curly bracket, where m is the sum of the masses of all of the particles. A continuous volume. If the mass distribution is continuous with the density ρ r within a solid Q, then the integral of the weighted position coordinates of the points in this volume relative to the center of mass r over the volume 5 is 0. That is, Q ρ r minus r d v equals 0. Display style IIINT limits underscore Q ρ math BF r math BF r math BF r dv equals 0 closing curly bracket. Solve this equation for the coordinates r to obtain r equals 1 m Q ρ r d v. Display style math BF r equals frac 1 m IIINT limit underscore Q ρ math BF r dv closing curly bracket, where m is the total mass in the volume. If a continuous mass distribution has uniform density, which means ρ is constant, then the center of mass is the same as the centroid of the volume. Barocentric coordinates. The coordinates are of the center of mass of a two-particle system, P1 and P2, with masses m1 and m2 is given by r equals 1 m1 plus m2 m1 r1 plus m2 r2. Display style math BF r equals frac 1 m underscore 1 plus m underscore 2 m underscore 1 math BF r underscore 1 plus m underscore 2 math BF r underscore 2 closing curly bracket. Let the percentage of the total mass divided between these two particles vary from 100% P1 and 0% P2 through 50% P1 and 50% P2 to 0% P1 and 100% P2. Then the center of mass R moves along the line from P1 to P2. The percentages of mass at each point can be viewed as projective coordinates of the point R on this line, and are termed barocentric coordinates. Another way of interpreting the process here is the mechanical balancing of moments about an arbitrary point. The numerator gives the total moment that is then balanced by an equivalent total force at the center of mass. This can be generalized to 3 points and 4 points to define projective coordinates in the plane and in space, respectively. Systems with periodic boundary conditions. For particles in a system with periodic boundary conditions, two particles can be neighbors even though they are on opposite sides of the system. This occurs often in molecular dynamics simulations, for example, in which clusters form at random locations and sometimes neighboring atoms cross the periodic boundary. When a cluster straddles the periodic boundary, a naive calculation of the center of mass will be incorrect. A generalized method for calculating the center of mass for periodic systems is to treat each coordinate, x and y and/or z, as if it were on a circle instead of a line. The calculation takes every particle's x coordinate and maps it to an angle theta I equals x I x m a x 2 pi. Display style theta underscore I equals frac x underscore I x underscore max 2 pi, where x max is the system size in the x direction and x I 0 x m a x. Display style x underscore I in 0 x underscore max closing curly bracket. From this angle, two new points, xi, I, zeta, I, display style, xi underscore I, zeta underscore I, closing curly bracket, can be generated, which can be weighted by the mass of the particle, x, I, display style x underscore I. For the center of mass given a value of 1 for the geometric center, xi, I, equals, cos, theta, I, times, m, I, display style, xi underscore I, equals, cos, theta underscore I, times m underscore I, zeta, I, equals, sin, theta, I, times, m, I, display style, zeta underscore I, equals, sin, theta underscore I, times m underscore I. In the xi, zeta, display style, xi, zeta, closing curly bracket, plane, these coordinates lie on a circle of radius 1. From the collection of xi, I, display style, xi underscore I, and zeta, I, display style, zeta underscore I, values from all the particles, the averages, xi, display style, overline, xi, and zeta, display style, overline, zeta, are calculated. These values are mapped back into a new angle, theta, display style, overline, theta, from which the x-coordinate of the center of mass can be obtained. Theta equals a t a n 2 minus zeta minus xi plus pi. Display style, overline, theta equals mathroom at in 2 overline zeta overline xi plus pi x c o m equals x m a x theta 2 pi. Display style x underscore com equals x underscore max frac overline theta 2 pi. The process can be repeated for all dimensions of the system to determine the complete center of mass. The utility of the algorithm is that it allows the mathematics to determine where the best center of mass is, instead of guessing or using cluster analysis to unfold a cluster straddling the periodic boundaries. It must be noted that if both average values are 0, xi, zeta, equals 0, 0, display style, overline, xi, overline, zeta, equals 00, closing curly bracket, then, theta, display style, overline, theta, is undefined. This is a correct result, because it only occurs when all particles are exactly evenly spaced. In that condition, their x-coordinates are mathematically identical in a periodic system. Center of gravity. A body's center of gravity is the point around which the resultant torque due to gravity forces vanishes. Where a gravity field can be considered to be uniform, the mass center and the center of gravity will be the same. However, for satellites in orbit around a planet, in the absence of other torques being applied to a satellite, the slight variation, gradient, in gravitational field between closer to, stronger, and further from, weaker, the planet could lead to a torque that will tend to align the satellite such that its long axis is vertical. In such a case, it is important to make the distinction between the center of gravity and the mass center. Any horizontal offset between the two will result in an applied torque. It is useful to note that the mass center is a fixed property for a given rigid body, e.g., with no slosh or articulation, whereas the center of gravity may, in addition, depend upon its orientation in a non-uniform gravitational field. In the latter case, the center of gravity will always be located somewhat closer to the main attractive body as compared to the mass center. and thus will change its position in the body of interest as its orientation is changed. In the study of the dynamics of aircraft, vehicles and vessels, forces and moments need to be resolved relative to the mass center. That is true independent of whether gravity itself is a consideration. Referring to the mass center as the center of gravity is something of a colloquialism, but it is in common usage, and when gravity gradient effects are negligible, center of gravity and mass center are the same and are used interchangeably. In physics, the benefits of using the center of mass to model a mass distribution can be seen by considering the resultant of the gravity forces on a continuous body. Consider a body Q of volume 5 with density ρ r at each point r in the volume. In a parallel gravity field, the force F at each point r is given by F r equals minus d m g k equals minus rho r d v g k. Display style math BF F math BF r equals dm g vec k equals rho math BF r dv g vec k. Closing curly bracket, where dm is the mass at the point r, g is the acceleration of gravity, and k is a unit vector defining the vertical direction. Choose a reference point r in the volume and compute the resultant force and torque at this point. F equals Q F r equals Q rho r d v minus g k equals minus m g k. Display style math BF F equals IIINT limit underscore Q math BF F math BF r equals IIINT limit underscore Q rho math BF r dv g vec k equals mg vec k. Closing curly bracket, and t equals Q r minus r times F r equals Q r minus r times minus g rho r d v k equals Q rho r minus r d v times minus g k. Display style math BF T equals IIINT limit underscore Q math BF r times math BF F math BF r equals IIINT limit underscore Q math BF r times g rho math BF r dv vec k equals left IIINT limit underscore Q rho math BF r dv right times g vec k. Closing curly bracket. If the reference point r is chosen so that it is the center of mass, then Q rho r minus r d v equals 0. Display style IIINT limits underscore Q rho math BF r dv equals 0. Closing curly bracket, which means the resultant torque T equals 0. Because the resultant torque is 0, the body will move as though it is a particle with its mass concentrated at the center of mass. By selecting the center of gravity as the reference point for a rigid body, the gravity forces will not cause the body to rotate, which means the weight of the body can be considered to be concentrated at the center of mass. Linear and angular momentum. The linear and angular momentum of a collection of particles can be simplified by measuring the position and velocity of the particles relative to the center of mass. Let the system of particles π I equals 1, n of masses m be located at the coordinates ρ with velocities v. Select a reference point r and compute the relative position and velocity vectors. r I equals r I minus r plus r v I equals d d t r I minus r plus v. Display style mathbf r underscore I equals mathbf r underscore I mathbf r plus mathbf r quad mathbf v underscore I equals frac d dt mathbf r underscore I mathbf r plus mathbf v. Closing curly bracket. The total linear and angular momentum vectors relative to the reference point are p equals d d t I equals 1 n m I r I minus r plus I equals 1 n m I v. Display style mathbf p equals frac d dt left sum underscore I equals 1 caret n m underscore I mathbf r underscore I mathbf r right plus left sum underscore I equals 1 caret n m underscore I right mathbf v. Closing curly bracket. And L equals I equals 1 n m I r I minus r times d d t r I minus r plus I equals 1 n m I r I minus r times v. Display style mathbf L equals sum underscore I equals 1 caret n m underscore I mathbf r underscore I mathbf r times frac d dt mathbf r underscore I mathbf r plus left sum underscore I equals 1 caret n m underscore I mathbf r underscore I mathbf r right times mathbf v. Closing curly bracket. If r is chosen as the center of mass, these equations simplify to p equals m v L equals I equals 1 n m I r I minus r times d d t r I minus r. Display style mathbf p equals m mathbf v. Quad mathbf L equals sum underscore I equals 1 caret n m underscore I mathbf r underscore I mathbf r times frac d dt mathbf r underscore I mathbf r. Closing curly bracket. Where m is the total mass of all the particles, p is the linear momentum, and L is the angular momentum. The law of conservation of momentum predicts that for any system not subjected to external forces, the momentum of the system will remain constant, which means the center of mass will move with constant velocity. This applies for all systems with classical internal forces, including magnetic fields, electric fields, chemical reactions, and so on. More formally, this is true for any internal forces that cancel in accordance with Newton's third law, locating the center of mass. The experimental determination of the center of mass of a body uses gravity forces on the body and relies on the fact that in the parallel gravity field near the surface of the Earth, the center of mass is the same as the center of gravity. The center of mass of a body with an axis of symmetry and constant density must lie on this axis. Thus, the center of mass of a circular cylinder of constant density has its center of mass on the axis of the cylinder. In the same way, the center of mass of a spherically symmetric body of constant density is at the center of the sphere. In general, for any symmetry of a body, its center of mass will be a fixed point of the symmetry. In 2 dimensions, an experimental method for locating the center of mass is to suspend the object from 2 locations, and to drop plumb lines from the suspension points. The intersection of the 2 lines is the center of mass. The shape of an object might already be mathematically determined, but it may be too complex to use a known formula. In this case, one can subdivide the complex shape into simpler, more elementary shapes, whose centers of mass are easy to find. If the total mass and center of mass can be determined for each area, then the center of mass of the whole is the weighted average of the centers. This method can even work for objects with holes, which can be accounted for as negative masses. A direct development of the planimeter known as an intergraph, or integerometer, can be used to establish the position of the centroid, a center of mass of an irregular, 2-dimensional shape. This method can be applied to a shape with an irregular, smooth or complex boundary where other methods are too difficult. It was regularly used by shipbuilders to compare with the required displacement and center of buoyancy of a ship, and ensure it would not capsize. In 3 dimensions, an experimental method to locate the 3-dimensional coordinates of the center of mass begins by supporting the object at 3 points and measuring the forces F1, F2, and F3 that resist the weight of the object. W equals minus weak. K is the unit vector in the vertical direction. Let A1, R2, and R3 be the position coordinates of the support points. Then the coordinates R of the center of mass satisfy the condition that the resultant torque is 0. T equals R1 minus R times F1 plus R2 minus R times F2 plus R3 minus R times F3 equals 0. Display style mathbf T equals mathbf R underscore 1 mathbf R times mathbf F underscore 1 plus mathbf R underscore 2 mathbf R times mathbf F underscore 2 plus mathbf R underscore 3 mathbf R times mathbf F underscore 3 equals 0. Closing curly bracket, or R times minus W K equals R1 times F1 plus R2 times F2 plus R3 times F3. Display style mathbf R times W VEC K equals mathbf R underscore 1 times mathbf F underscore 1 plus mathbf R underscore 2 times mathbf F underscore 2 plus mathbf R underscore 3 times mathbf F underscore 3. Closing curly bracket. This equation yields the coordinates of the center of mass R asterisk in the horizontal plane as R equals minus 1 W K times R1 times F1 plus R2 times F2 plus R3 times F3 display style mathbf r caret asterisk equals frac 1 w vec k times mathbf r underscore 1 times mathbf f underscore 1 plus mathbf r underscore 2 times mathbf f underscore 2 plus mathbf r underscore 3 times mathbf f underscore 3. Closing curly bracket. The center of mass lies on the vertical line L, given by L T equals R plus T K. Display style L T equals mathbf R caret asterisk plus T vec K. Closing curly bracket. The three-dimensional coordinates of the center of mass are determined by performing this experiment twice with the object positioned so that these forces are measured for two different horizontal planes through the object. The center of mass will be the intersection of the two lines L1 and L2 obtained from the two experiments. Applications. Engineers try to design a sports car so that its center of mass is lowered to make the car handle better. When high jumpers perform a Fosbury flop, they bend their body in such a way that it clears the bar while its center of mass does not necessarily clear it. Aeronautics. The center of mass is an important point on an aircraft, which significantly affects the stability of the aircraft. To ensure the aircraft is stable enough to be safe to fly, the center of mass must fall within specified limits. If the center of mass is ahead of the forward limit, the aircraft will be less maneuverable, possibly to the point of being unable to rotate for takeoff or flare for landing. If the center of mass is behind the aft limit, the aircraft will be more maneuverable, but also less stable, and possibly so unstable that it is impossible to fly. The moment arm of the elevator will also be reduced, which makes it more difficult to recover from a stalled condition. For helicopters in hover, the center of mass is always directly below the rotor head. In forward flight, the center of mass will move forward to balance the negative pitch torque produced by applying cyclic control to propel the helicopter forward. Consequently, a cruising helicopter flies nose down in level flight. Astronomy. The center of mass plays an important role in astronomy and astrophysics, where it is commonly referred to as the barycenter. The barycenter is the point between two objects where they balance each other. It is the center of mass where two or more celestial bodies orbit each other. When a moon orbits a planet, or a planet orbits a star, both bodies are actually orbiting around a point that lies away from the center of the primary, larger body. For example, the moon does not orbit the exact center of the Earth, but a point on a line between the center of the Earth and the moon, approximately 1,710 kilometers, 1,062 miles, below the surface of the Earth, where their respective masses balance. This is the point about which the Earth and Moon orbit as they travel around the Sun. If the masses are more similar, e.g., Pluto and Charon, the barycenter will fall outside both bodies. Kinesiology. In kinesiology and biomechanics, the center of mass is an important parameter that assists people in understanding human locomotion. The human body's center of mass is always changing because it is not a fixed shape. Typically, a human's center of mass is detected with a reaction border, the segmentation method. The reaction board is a static analysis that involves the person lying down on the reaction board and using the static equilibrium equation to find the center of mass. The segmentation method is a mathematical solution that states that the summation of the torques of individual body sections relative to a specified axis must equal the torque of the whole body system relative to the same axis. Rock balancing. In rock balancing, The stability of a collection of rocks is related to its center of mass in relation to its resting point. Contact points of the rocks. See also. Notes. Barron, Margaret E. 2004. 1969. The Origins of the Infinitesimal Calculus. Courier Dover Publications. ISBN 0-486-49544-2. Beatty, Millard F. 2006. Principles of Engineering Mechanics. Volume 2. Dynamics. The Analysis of Motion. Mathematical Concepts and Methods in Science and Engineering. 33. Springer. ISBN 0-387-23704-6. Feynman, Richard. Layton, Robert. Sands, Matthew. 1963. The Feynman Lectures on Physics. Addison Wesley. ISBN 0-201-021161. Federal Aviation Administration. 2007. Aircraft Weight and Balance Handbook. PDF. United States Government Printing Office. Retrieved 23 October 2011. Giambattista, Alan. Richardson. Betty McCarthy. Richardson. Robert Coleman. 2007. College Physics. 1. 2nd ed. McGraw-Hill Higher Education. ISBN 0-07-1106-081. Goldstein. Herbert. Paul. Charles. Safko. John. 2001. Classical Mechanics. 3rd ed. Addison Wesley. ISBN 0-201-65702-3. Hamill, Patrick. 2009. Intermediate Dynamics. Jones and Bartlett Learning. ISBN 978-0-7637-57281. Klepner, Daniel. Kolenkov. Robert. 1973. An Introduction to Mechanics. 2nd ed. McGraw-Hill. ISBN 0-07-035048-5. Levi, Mark. 2009. The Mathematical Mechanic. Using Physical Reasoning to Solve Problems. Princeton University Press. ISBN 978-0-691-14020-9. Mancazu, Paolo. 1999. Philosophy of Mathematics and Mathematical Practice in the 17th Century. Oxford University Press. ISBN 0-19-513244-0. Murray, Carl. Dermot, Stanley. 1999. Solar System Dynamics. Cambridge University Press. ISBN 0-521-57295-9. Sangwin, Christopher J. 2006. Locating the Center of Mass by Mechanical Means. PDF. Journal of the Orchid Society. 15. 2. Retrieved 23 October 2011. Shaw, Stephen N. 2008. Forces in Physics. A Historical Perspective. Greenwood Press. ISBN 978-0-313-33303-3. Simon, Keith R. 1971. Mechanics. 3rd ed. Addison Wesley. ISBN 0-201-07392-7. Van Pelt, Michael. 2005. Space Tourism. Adventures in Earth Orbit and Beyond. Springer. ISBN 0-387-40213-6. Walton, William. 1855. A Collection of Problems in Illustration of the Principles of Theoretical Mechanics. 2nd ed. Dayton, Bell and Co. Asimov, Isaac. 1988. 1966. Understanding Physics. Barnes & Noble Books. ISBN 0-88029-251-2. Beatty, Millard F. 2006. Principles of Engineering Mechanics. Volume 2. Dynamics. The Analysis of Motion. Mathematical Concepts and Methods in Science and Engineering. 33. Springer. ISBN 0-387-23704-6. Feynman, Richard. Layton, Robert B. Sands, Matthew. 1963. The Feynman Lectures on Physics. 1. 6th printing. February 1977 ed. Addison Wesley. ISBN 0-201-02010-6. Frauchi, Stephen C. Olenek, Richard P. Apostol, Tom M. Goodstein, David L. 1986. The Mechanical Universe. Mechanics and Heat. Advanced Edition. Cambridge University Press. ISBN 0-521-30432-6. Goldstein, Herbert, Paul, Charles, Safko, John. 2002. Classical Mechanics. 3rd ed. Addison Wesley. ISBN 0-201-65702-3. Goodman, Lawrence E. Warner, William H. 2001. 1964. Statics. Dover. ISBN 0-486-42005-1. Hamill, Patrick. 2009. Intermediate Dynamics. Jones and Bartlett Learning. ISBN 978-0-7637-57281. Jong, I. G. Rogers. B. G. 1995. Engineering Mechanics. Statics. Saunders College Publishing. ISBN 0-03-026309-3. Millikan, Robert Andrews. 1902. Mechanics, Molecular Physics and Heat. A 12 weeks college course. Chicago. Scott, Forsman and Company. Retrieved 25 May 2011. O'Donnell, Peter J. 2015. Essential Dynamics and Relativity. CRC Press. ISBN 978-1-466-58839-4. Pollard, David D. Fletcher, Raymond C. 2005. Fundamentals of Structural Geology. Cambridge University Press. ISBN 0-521-83927-0. Peitel, Andrew. Kearsalas, John. 2010. Engineering Mechanics. Statics. 1. 3rd ed. Cengage Learning. ISBN 978-0-495-29559-4. Rosen, Joe. Gothard, Lisa Quinn. 2009. Encyclopedia of Physical Science. Infobase Publishing. ISBN 978-0-8160-7011-4. Surway, Raymond A. Jewett, John W. 2006. Principles of Physics. A Calculus-Based Text. 1. 4th ed. Thomson Learning. ISBN 0-534-49143-X. Shirley, James H. Fairbridge. Rhodes Whitmore. 1997. Encyclopedia of Planetary Sciences. Springer. ISBN 0-412-06951-2. De Silva, Clarence W. 2002. Vibration and Shock Handbook. CRC Press. ISBN 978-0-8493-1580-0. Simon, Keith R. 1971. Mechanics. Addison Wesley. ISBN 978-0-201-07392-8. Tipler, Paul A. Mosca, Jean. 2004. Physics for Scientists and Engineers. 1A. 5th ed. W. H. Freeman and Company. ISBN 0-7167-0900-7. Vint. Peter. 2003. Lab. Center of Mass. Center of Gravity of the Human Body. PDF. Kin 335 Biomechanics. Retrieved 18 October 2013. Motion of the center of mass shows that the motion of the center of mass of an object in free fall is the same as the motion of a point object. The Solar System's barycenter. Simulations showing the effect each planet contributes to the Solar System's barycenter. Center of gravity at work. Video showing objects climbing up an incline by themselves.